Today we're going to be covering optimization. And so this is a really neat application of finding maximums and minimums. And to verify that we are finding maximums and minimums, sometimes we'll be using the closed interval test, sometimes the first derivative test, and sometimes the second derivative test. It'll really just depend on the problem. But rather than looking at all these steps right now, let's just jump right into an example so you can get an idea of what everything on page 1 actually means. So example 1, find two positive numbers whose product is 100 and whose sum is minimum. So first of all, we're given that we have two positive numbers. So what we need to do first is pick a variable for these two numbers. So let's maybe say x and y. Okay. And so if that's what we're going to say, let me zoom in a little bit. We're going to say x and y are these two numbers. Then if their sum is supposed to be minimum, let's actually introduce another letter, s. So we have s is equal to x plus y, okay, whose sum is minimum. So this is what's going to be called our objective function. And you won't have to label this every time, but you might find it to be helpful in the beginning. And there's another equation that we want to write down here. And we won't always need to write down another equation, but I want to explain the need here for another equation. So we would like to minimize or maximize this function, which is going to consist of taking a derivative. Well, how are we going to take the derivative of this function of two variables? Okay. Well, there is actually a way that you'll learn in Calculus 4 that you could technically use here. You could use some partial derivatives. But rather than doing that, what we can do is we could use what we're going to call a constraint equation. It's going to be some equation that's going to allow us really to rewrite our objective function in terms of one independent variable. So next, let's read the first part here again. Find two positive numbers whose product is 100. So we also know x times y is equal to 100. And again, this is our constraint equation. And let's go ahead and solve this thing here for x or for y. It's really up to us. Let's go ahead and solve it for, how about y? So we're going to take that constraint and we're just going to divide each side here by x. All right, there's a good start. Next, we'll take this and we'll plug this into the objective function. So s is going to be equal to x plus 100 over x. Okay. Now, how do we solve this equation here for x instead of y? Our equation over here, it could look a little bit different, but we'll wind up getting the same results here. Next is what we have now is we have our objective function written in terms of just one independent variable. And so we can start taking the derivative of this thing to try and find the minimum. Okay. But before I do that, I want to point out, well, what's the domain of this function? What's the domain of this? And the domain can actually come from literal problems with plugging values of x in, like for instance here, we know we don't want to plug in x equals 0 because this would be undefined. But we were also told positive numbers, right? So you know x needs to be bigger than 0. So we can just automatically say, well, hey, let's go from 0 on. So this is actually the domain that we're looking at here. And I want to leave a little bit of space so I can actually write that. domain. But again, I'm not going to include the minus infinity to 0 because we only care about positive numbers. Okay, that's all we care about here according to our directions. Okay. All right. This means, though, we don't have a closed interval, right? So we will not be using the closed interval test. So that means to solve this problem, we're going to wind up either using the first or second derivative test. I oftentimes lean towards the second derivative test because I don't really enjoy drawing the number line with the first derivative test. So we're going to make an attempt here to use the second derivative test. And before you can find the second derivative, you need the first derivative. All right, so the derivative of x is 1. And then here, you really have x to the minus 1. So this is going to become minus 100 x to the negative 2 using the power rule. And before we move on, right, we want to find the critical points. Those are what we're going to plug into the second derivative. Okay. So to find the critical points, I need to think about, well, where is this thing undefined and where is it equal to 0? Well, if I were to rewrite this maybe just a smidge here, you'd see that this is really 1 minus 100 over x squared. Okay. And you can see actually one of the places where this is undefined is at x equals 0. Okay, at x equals 0. That would be one of our critical points if we were including 0 in the domain. But remember, x equals 0 makes our objective function undefined. So again, it's not part of our domain. So next thing, let's think about where it's 0 then. Let's go ahead and set this equal to 0. So if 0 equals 1 minus 100 over x squared. And if we add the, actually let's move this around a little bit. We have 1 is equal to 100 over x squared. Okay. And then one more step here. Let's multiply each side by x squared. So we have x squared equals 100. And what that tells us is x is equal to plus or minus 10. Right? Well, we don't care about, I'm actually going to write them both out all the way. X equals 10, minus 10 or x equals 10. Again, our domain though was just 0 to infinity. So this is not one of our critical numbers. So we actually got rid of 2 of our 3 critical numbers. One of them was 0, which wasn't in the domain, and one was x equals minus 10, which wasn't in the domain. So we only have one critical number here, x equals 10. Check, check, check. Check, 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 check. Hello, hello, hello. All right, so the next step here is going to be finding our second derivative. So we have s double prime is equal to, so remember this was 1 minus 100x to the minus 2. So the derivative of just 1 by itself there is 0. And if we use our power rule, this is going to become 200 x to the, minus 3. There's something interesting about this second derivative. Okay? And that thing that's interesting is that if x is any number from 0 to infinity, then we know something about this second derivative. What is that? Well, if x is some positive number, then you have 200 times some positive number to the negative 3, which will always be bigger than 0. So what we have is the second derivative is greater than 0 for all x in 0 to infinity. And let's think about what this tells us. Okay. If this is concave up on its entire domain, 0 to infinity, it could look, something like this. Except for maybe we have a vertical asymptote there. Okay. Might look something like this. And so now you can kind of see, well, if it's concave up everywhere and you have a critical point, which looks like it's maybe right in here. If you have a critical point on a graph that's concave up everywhere, then that point is going to be a absolute minimum. And so this is a little bit different than what the second derivative test tells us. The second derivative test would have told us that if we plugged in x equals 10, right? And you can see, again, based on what we've written up above, this number would be something bigger than 0. And again, since that second derivative at 10 is bigger than 0, we would know, hey, there is a local minimum at x equals 10. But because this is concave up over its entire domain, we know that this is actually an absolute minimum. So that's what I'm going to write here. Let me get rid of all this extra stuff here. Thus, we have an absolute minimum at x equals 10. Now, the last thing that I want to say here is that, yes, this is not exactly the same thing as our second derivative test, but it's using the same concepts. Okay. And so what's going to happen in all the problems that we're going to do in this section is either the concavity will be always concave up or always concave down on some open interval. And if that's the case, you'll know that your critical point applies or is associated with a absolute maximum or minimum, which is what we're looking for here in optimization. We want absolute minimums, absolute maximums, and not local. Now, to finish this problem, we need to find both the numbers, x and y. Okay? And so note, so far we just have x equals 10. How do we find that y value? Well, it's going to come from our constraint. All the way up here. Remember, x times y needed to equal 100, and y was equal to 100 over x. Okay? So, okay, and so this is actually our final answer here. The two numbers that we were looking for were x equals 10, y equals 10.